For about 100 years, we had Tyrannosaurus rex almost completely backward. The creature standing in natural history museums around the world, the one in every textbook your kids grew up with, the one stomping through Jurassic Park, that version of T-Rex was built mostly on assumption. Scaled-up lizard, cold-blooded, slow, practically blind unless you moved, covered in green scaly skin. Nearly every one of those details turned out to be wrong. And the real animal, the one paleontologists have been piecing together over the last 3 decades, is stranger and in some ways more impressive than the monster we invented. The first reasonably complete T-Rex skeleton was found in 1902 by Barnum Brown, a fossil hunter working for the American Museum of Natural History in Montana. Brown found more T-Rex bones than anyone else in history, and the skeleton he assembled in New York became the template for everything that followed. The problem was that assembling a skeleton from fragments scattered across rock formations tells you a lot about bone structure and almost nothing else. No skin, no color, no behavior, no sound. All of that had to be guessed, and the guesses reflected what scientists already believed about reptiles in general, which in 1902 meant slow, cold, and scaly. The scientific community spent most of the 20th century building on those early assumptions without seriously questioning them. By the time Jurassic Park came out in 1993, the movie was actually incorporating some newer science around speed and behavior. But the skin, the posture, and several other key features were still based on decades-old guesses that were already starting to fall apart. What changed everything was a combination of new fossil discoveries in China, advances in molecular analysis, and a general shift in how paleontologists thought about the relationship between dinosaurs and modern birds. Once researchers started treating T-Rex not as a giant lizard, but as a very large bird ancestor, the entire picture began to change, and once it started changing, it did not stop. The feather question is probably the most uncomfortable revision for people who grew up with a certain image of T-Rex, so it is worth being careful about what the evidence actually shows. We know that many close relatives of T-Rex had feathers. Eutyrannus huali, a large tyrannosaur from northeastern China discovered in 2012, was found with clear impressions of long filamentous feathers preserved in the rock around its bones. It was about 9 meters long and lived about 125 million years ago. That is significantly earlier and somewhat smaller than T-Rex, but it is close enough on the family tree to matter. On the other side of the argument, a 2017 study published in the journal Biology Letters examined fossilized skin impressions from several T-Rex specimens, including sections of the neck, pelvis, and tail. Those impressions showed scales, not feathers, at least in those areas. The current thinking among most paleontologists is that adult T-Rex was probably mostly scaled, but may have retained some feathery covering, particularly on the back and upper body, the way some large modern birds have bare legs but feathered torsos. Young T-Rex individuals may have had more extensive feather coverage that was shed as they grew. Honestly, the full picture is still being worked out. The evidence points toward an animal that was somewhere between fully scaled and fully feathered, with the balance probably shifting depending on age and the specific part of the body. Not the clean answer anyone was hoping for, but that is where the science sits right now. Jurassic Park made the T-Rex chase seem terrifyingly plausible. A jeep driving at around 45 miles per hour, and the animal is right there. It turns out that scene required significant creative license. Biomechanical studies over the last 20 years have come to a fairly consistent conclusion about T-Rex speed. A 2002 study by John Hutchinson at the Royal Veterinary College in London calculated that for a T-Rex to run at speeds comparable to a large modern predator, the leg muscles would need to make up roughly 86% of the animal's total body mass, which is anatomically impossible. Later work, including a 2017 paper in Piaget, used computer modeling of the skeleton and concluded that T-Rex likely moved at a brisk walking speed of around 12 miles per hour, which is about the pace of a fast human jogger. Running, meaning a full gallop with both feet off the ground simultaneously, was probably not possible at all given the bone structure and the animal's estimated weight of around 9 tons. What T-Rex almost certainly had instead of speed was endurance. It could cover enormous distances at a steady pace, and its prey animals were not necessarily faster. The hadrosaurs and ceratopsians it hunted were also large and heavy. It also almost certainly scavenged when the opportunity presented itself, which is behavior that requires persistence and range, not sprinting ability. The idea that T-Rex could not see you if you stood still came from a misreading of studies on the visual systems of reptiles and was never really supported by the fossil evidence. The actual analysis of T-Rex skull structure tells a different story entirely. Kent Stevens, a computer scientist at the University of Oregon, published research in 2006 examining the orientation of the eye sockets in T-Rex skulls. He found that T-Rex had a degree of binocular overlap, meaning the field of view where both eyes could focus simultaneously of about 55 degrees. That is comparable to a modern hawk and significantly better than most other dinosaurs. For comparison, humans have a binocular overlap of about 120 degrees, but our depth perception is not dramatically better than a hawk's at distance. T-Rex could judge distance accurately and see clearly at range. Its sense of smell was likely even more extraordinary. The olfactory bulbs, the structures in the brain dedicated to processing scent, were proportionally enormous. A 2008 study comparing the brain endocasts, basically the impressions left inside fossil skulls, of multiple dinosaur species found that T-Rex had olfactory bulbs larger relative to its brain size than almost any other theropod examined, larger even than modern vultures, which are famous for their ability to locate carcasses from miles away. T-Rex almost certainly knew you were there long before it could see you. The arms have become a cultural joke, and they deserve a more serious look. Yes, T-Rex arms were short. At roughly 3 feet long on a 40-foot animal, they look almost absurd, but they were not weak. The bone structure and the attachment points for muscles on known T-Rex specimens indicate that each arm could exert a force of around 430 pounds. They could not reach the mouth. They could not reach each other. But they were heavily built and apparently useful for something. The most credible current hypothesis is that the arms functioned as anchoring hooks during feeding, holding a struggling carcass in place while the jaws did the work. Another possibility is that they helped the animal rise from a resting position on the ground. There is also a 2022 paper published in Acta Paleontologica Polonica by paleontologist Kevin Padian that proposed the arms may have been used during mating. Whatever their specific function, the muscle mass and bone density suggest these were not vestigial structures on their way to disappearing. They were doing something important enough to maintain across millions of years of evolution. For most of the 20th century, dinosaurs were treated as cold-blooded reptiles, meaning their body temperature was regulated by external heat, like modern lizards. That classification has been overturned fairly comprehensively in recent decades. In 2020, a study in the journal Nature used isotopic analysis of T-Rex tooth enamel to measure the temperature at which the enamel formed, and found that T-Rex maintained a body temperature around 38 to 40 degrees Celsius. That is in the warm-blooded range, close to a modern large mammal. The growth rings visible in T-Rex bones also indicate rapid growth rates consistent with warm-blooded metabolism rather than the slow growth seen in cold-blooded animals. The social behavior question is more open. There is limited but genuinely interesting evidence suggesting T-Rex may not have been a completely solitary animal. A site in Utah called the Rainbows and Unicorns Quarry, described in a 2021 paper in Peer J, contained the bones of at least 2 adult and 1 juvenile T-Rex in association, along with evidence suggesting they may have died together. This does not prove pack behavior, but it raises the possibility. Evidence of parental behavior in close tyrannosaur relatives is somewhat stronger, and given how thoroughly T-Rex has been revised in other areas, ruling out social complexity entirely at this point seems premature. Pulling all of this together, the current best reconstruction of T-Rex looks quite different from the version that became famous in the 20th century. The posture alone was corrected years ago. Early reconstructions showed T-Rex upright, nearly vertical, with the tail dragging on the ground. The actual bone structure, particularly the hip joints and vertebral column, makes that posture impossible. T-Rex walked horizontally, body roughly parallel to the ground, tail held out behind as a counterbalance to the heavy head, much more like a large bird than the kangaroo-like stance of old museum displays. The skin question remains partially open, but the combination of scaled skin impressions and feathered relatives suggests a patchwork animal, possibly with scaly flanks and belly and some degree of feathery or bristly covering along the back. A 2023 study published in Science Advances examined the skull structure in detail and found evidence suggesting T-Rex likely had lips covering its teeth, similar to a modern monitor lizard, rather than the permanently exposed fangs of the movie version. The authors argued that the teeth, despite their size, showed very low wear consistent with being kept moist and covered, rather than constantly exposed to air. And the sound, the famous roar, was probably not a roar at all. Birds, which are the living descendants of theropod dinosaurs, do not roar. Crocodilians, the closest living relatives of dinosaurs among reptiles, produce low-frequency rumbles and hisses. The most current thinking is that T-Rex likely produced deep closed-mouth vocalizations, low-booming sounds that could travel long distances, rather than the high-pitched scream that film sound designers invented in the 1990s. Every one of these revisions came from better evidence and better questions, not from scientists deciding to rewrite history for its own sake. The animal that actually lived 68 million years ago in what is now Montana and the Dakotas was warm-blooded, sharper-sighted than we gave it credit for, possibly partially feathered, slower than the movies suggested, and almost certainly far more complex behaviorally than a giant cold-blooded predator. It is a more interesting animal than the one we invented, which is usually what happens when the evidence catches up to the assumption. The question worth sitting with is what other animals from deep time we are still getting significantly wrong, and what the next round of discoveries is going to change. If you watched this far, thank you. Leave a comment below with which revision surprised you most. Like the video if you found it worthwhile, and subscribe so you see the next one.